All right. We got to practice these to get good. So a few more examples here. Calculate the derivative of the function g of x equal to negative 5 divided by x to the power 4. All right, so we see a fraction here. We got to use quotient rule. Or do we? No, we actually don't. So we see a fraction, but when we look at the pieces of this fraction, there's only a variable term in the bottom. There's no variable up here. This is just a constant. So this negative 5 is just a constant multiple. So we actually do not need to use the quotient rule here. So there's a fraction, yeah, but the variable, there's only a variable in the bottom here. So there is a fraction, but there's only a variable on one side of that fraction. In this case, it's down here. We would do something similar if it was reversed. So if there was a variable term up here and just a constant down here, you don't have to use quotient rule then. You would just kind of break apart the fraction. And really, this is what we're going to do. We have this fraction. We're going to separate this constant piece from the actual variable part. And so we can rewrite this. Just rewrite our function as negative 5 times 1 over x to the 4. And we can even rewrite this further then. We know with fractions like this, we can rewrite that as a power function using a negative exponent. One of our common strategies for dealing with these power functions. So what do we get if we do that? We get negative 5 times x to the negative 4. And so when we differentiate this, this is now just a power rule problem. So how do we do it? Well, we look at our power function part. We take the negative 4, the exponent, bring it down, multiply it with the constant that's in front. So we're going to end up with a positive 20. So negative 5 times negative 4 is positive 20. Our variable stays the same, so x. And then we're going to take this negative 4, our old exponent, and we subtract 1. So we go from negative 4 down to negative 5. And there's our derivative. No quotient rule necessary. Now, you could do quotient rule. You still could do it. You'd still get the right answer, just a lot more work in this case. So it's not wrong to use the quotient rule here. It's just that it's not necessary. It's not needed. It's too much. So product or power rule here is probably the easier way to go. So when you see a fraction like this and you see a variable term in just the denominator, no variable in the top, break apart the fraction. So take the constant term, separate it from the variable part, so negative 5 times 1 over x to the 4, and then use a negative exponent to rewrite that fraction. And we did that here, negative 5 times x to the minus 4. And now this is a much easier version of our function to differentiate. All right, so quotient rule not necessary. You still could do it though. And yeah, let's see what it looks like, because sometimes I do see people try to do quotient rule here, and there's one little trick or one little kind of point where you might get tripped up. So let's say we didn't notice that we could do it this easier way. This is how I would recommend you do it. Let's say we were going to do quotient rule. How would that look? Well, let's implement the quotient rule. So we write down our quotient here as a product, so top times the bottom. And then do 2 copies of that, top times the bottom. And then in the first copy, we apply the derivative to just the first part. In the second copy, we apply the derivative to just the second part. and then we put a minus sign in between here. And we're going to end up with a double negative, so I'll put parentheses around there. And then we draw a big fraction sign, and we square the original denominator. So it was x to the fourth. We're going to square that thing. And if you do quotient rule, you're going to get the same answer. It's going to look more complicated until you simplify it down. But the one area sometimes people that use this way kind of make a mistake on is right here, this -5 derivative. When we differentiate this -5, it's just a constant. So when we differentiate this, this is 0. So this whole first piece here is going to become just 0 once we actually continue on with the differentiation. So this -5, if we differentiate that, becomes 0. So we end up with 0 times x to the 4. And that's just 0. So we're going to have something left over from here. We could simplify this x to the 4th squared, make that x to the power 8. And then you could keep differentiating and going from there. But this is how it would look if you were going to do quotient rule. I wouldn't recommend this. I would say try to rewrite the function first. This is much easier. But if you did quotient rule, perfectly fine. Just be careful of this derivative of a constant term. It's easy to kind of miss this. All right, so sometimes we can get away using negative exponents, say, to rewrite our function. In the next one, we have this function capital F of x equal to 3x squared plus 2 times the square root of x, all divided by x. And here we do have a fraction. And if we look, there is a variable down here, and there are some variables up here. So on the surface, this looks like quotient rule is needed. But we can actually do the division first. So we've seen this with multiplication and product rule. Sometimes you can just multiply things out, and then you don't have to do the product rule. In this case, we can actually just do the division. That way we don't have to use quotient rule. So if we rewrite this function, we're going to do the division first. So it's just one of those little algebraic strategies. So you actually look to see if you can simplify the function first. And so the way we can rewrite this function is we can break this up into 2 separate fractions. So we can write this as 3x squared over x, and then plus 2 square root x over x, and then simplify. So 3x squared divided by x is just 3x. And then here, the square root x and the divided by x here, we would want to rewrite that square root term as x raised to the 1/2 power. And so we're going to end up, when we actually do the simplification here, we're going to end up with x raised to the -1/2. So this is really x raised to the 1/2 right here. And when we divide powers of x, we subtract the exponents. So we have a 1/2 from here, and then there's a kind of a hidden exponent of 1. So 1/2 minus 1 would give us the -1/2. So simplifying this first fraction is 3x, simplifying that second fraction is 2x to the -1/2. And now there's no division. We just have these power functions to differentiate. So now we can just do it. So what would it look like? Well, f prime of x in this case, derivative of 3x is just 3. And then we got to use some power rule on this other term here. So we're going to, well, let me hold off on the plus sign. Normally that carries through, but we're going to end up, we have a negative exponent here. So we take the old exponent, -1/2, bring it down, multiply it with that constant in front. So we end up with 2, positive 2 times -1/2. So that's just going to be -1. We keep our variable the same, x, and then we take that old exponent and subtract 1. So we go from -1/2 down to -3/2. And There we go. There's our derivative. No quotient rule necessary. So we were able to just use the power rule here to differentiate this. So in these two little examples here, sometimes we can get away without having to use quotient rule. First case, we are able to just rewrite it as a power function. Second case here, we were able to do the division first, so that we ended up with kind of two power functions being added together, and we're just able then to use power rule. All right, so just kind of little things, little tricks here to kind of keep in mind as you're practicing these quotient rule problems. All right, so that's going to do it for quotient rule. In the next lesson, another rule. Another one of our major derivative rules. So we've seen product rule, we've seen quotient rule, and now we're getting to chain rule. And this one's going to be kind of the more complicated of the three. So this one's going to take a little bit of work. So we'll see you there. Bye-bye.